Okay, but you get the point of it? This is going up and then coming. Let me see if I can take one of those away. Oh, take the whole thing away. Okay. So I've got something like this. Now, where do you think this derivative is going to peak? Have an extrema. I think so too. Now, how far up it goes, I don't know, but it's going to peak there. Why would you say at 1? What else do you think happens at 1? Change in concavity, known as the inflection point. Yeah, so I'm thinking it's going to peak right about there and then come down here, and then it continues on. So the first derivative is increasing where? From negative infinity to 1, it's decreasing where? From 1 to... Isn't that an interesting way to look at that graph? It kind of plays with your mind a little bit. Now, let's see here. Would you take your inspires? And we're going to actually put this function. I didn't tell you what the function was. I'm going to tell you now. Okay? I want you to look at this. And the function is, here we go. Well, I'm going to tell you because evidently something is not. Okay, be that way. I'll tell you, and you guys can work ahead, and I'll work on mine up here. Oops, that one's good. Okay. Okay, I'm going to put in a graph, and it is negative 1/2 x squared times x minus 3. Now you might need to put a multiplication in here, so I'm going to just go ahead and do that anyway. We should see the graph that I'm showing you there. Whoops, what doesn't it like? Yeah, it didn't like it down there. Okay. The window, let's just go ahead and do a window so we have that. Let's see, the window is negative 3 to 4, scale 1, and negative 3 to 3, scale 1. Okay, so there's the curve that I gave you. I could have you compute or determine the derivative, but let me just kind of give it to you here. Well, no, let's do it this way. Go to the template, so control, on this model, control the multiplication. On the black one, you just got your own key, the template key, and let's do the derivative with respect to x of what? F1 of x, right? We'll let it do all the work for us. Okay, and I'm going to change the attributes. I'm going to change mine to be we'll do that. Okay, there's my derivative. Is that what we determined it to be? Okay, let's do one more thing. Let's analyze the second derivative. Now, if you analyze the second derivative, which of these curves are we going to be going through and talking about? So, any place on this derivative that you think might be of interest on the second derivative? Again? Yeah. So what's going to happen on the second derivative at this point? It'd be a 0. I should have a point right down here. And to the what's that direction to you? To the right of that? Okay, to the right of that, are we going to have second derivative values above or below the input? Why would it be above? Did you say above? Oh, you said below. I'm sorry. Yeah, below, because if you think about tangents to this, they'd be negative slopes. Yeah. So you can analyze those a lot. Now, what happens? Let's see. The inflection point should be right there at 1. Let's see if that's actually true. I'm going to go over here to menu. I'm going to analyze. I'm going to get a maximum of this curve. And right there it is, right where I thought it was, which would correspond to an inflection point right down here. Okay? Well, be aware that those are some fun ones, but they're also ones that you can really, I can test you on whether or not you truly understand. Okay, we've got 15 minutes. I'm really anxious to get to the next few problems, so let's move on. Consider a college student who works from 7 p.m. to 11 p.m., called the second shift, for those of you who know anything about factory times here, assembling mechanical components. The number n of components assembled after t hours is given by. Who thought up this equation? Who says that's what it is? Cole, did you say that? Sure, somebody who's looking at data. You know, I keep bringing you back to that because we get this idea that somehow mathematics is only for those people who sit in a math class, when in fact they're out there considering how many components can be assembled by a college student on second shift after t hours of being on board there. At what time is a student assembling components at the greatest rate? At what time? What do you think you need to determine? The derivative. And when you're considering the derivative, you want to know, now the rate is, you know, how fast is the, at what rate, excuse me, is are the components being assembled, but we want to know what the greatest rate is. So are we just looking at the first derivative? We're actually looking at the second derivative. We want to know where's the maximum on the rate function. You know, how fast are they assembling these? But we don't want to know that. We want to know what's the greatest rate. So we need to actually look at the second derivative. So we need to find the first derivative with respect to t. Make sure you've got that. Go ahead and work on it. I'm going to do my work up here. You know, you can stop at any point and take the second derivative. But I like to go, make it as clean as possible. And so I'm going to continue working on this, hoping I don't make any errors along the way. Is that truly as nice as it is? By golly, it is. See how nice it is to go ahead and finish it up? Those 40t cubes cancel out. because of the, okay. So this is going to tell me the rate at which components are assembled. But I don't want that, do I? This is kind of getting us into that next section called optimization. We want to optimize this rate. And so now I need to look at the second derivative. What might make this work a little easier? Anyone do something different to start this? I'll tell you, if I squared that binomial, it might have made it a little easier. Did anyone try that? You might want to. Keep that tucked away as something that might have helped. Whoops, can't do that yet. I did a couple of things together in this step, I have to admit. For those of you who might go back and look at this, I took the derivative of this as 2 times t, and I took the 2 times 2 and made it 4. That may be too confusing. Let me go ahead and not be so anxious here. We'll put the 2 there and the 2t here. When I get this all done, what am I really wanting to find out? You know, it's kind of like, I get this derivative, so what? What am I trying to find? What am I trying to do? Trying to maximize it. Yeah, and I'm going to maximize it by looking at what? I'm sorry, what was that again? Yeah. So, you know, at some point I'm going to set this equal to 0. Now, I can decide where I want to do this, when I want to do this. You know, I'm going to factor out a 4t squared and 160, and that's going to leave me with a 4 plus t squared from the first one, minus 4t squared. You know, I'm just as likely as you are to drop some terms here. So I'm going to have to make sure that I do a check on it. I'll take that out. I have 1 left. I'll take the 160 out, and then I've got the 2 times 2 is 4. I have the t squared. I took that out. I think I've got that. I know someone's watching. I can take one of those away from here. So I have 160 times 4 plus t squared minus 4t squared divided by 4 plus t squared cubed. You know, you got to check this stuff. What happened to the t?